Okay, so now we're looking back again at the instantaneous rate of change with this limit operator. Okay, so if we apply the limit operator to the expression for average rate of change, the arc, we can determine the instantaneous rate of change exactly. Okay, so this is our formula that we had, where a is some value x, where we want the instantaneous rate of change at for that function. Okay. So let's go through here and try to determine the average rate of change for x squared from a to a plus h. Okay, so if we do that, going through this formula, okay, and we've got this a plus h squared minus a squared, just substituting a plus h in for x squared, okay, and we get this expression. The a squareds cancel out, and you've got this expression. And then once you try to simplify that, you get 2a plus h, where h cannot equal 0. So that's the average rate of change from some point a to a plus h. Okay, so if you were to take a look at this x squared function, and say a is there and a plus h is there, then you got a point there and a point there, and the average rate of change is the slope of that secant. Okay, slope of that secant. And so that's what we're looking for here. So now we have a formula that will give us the average rate of change for any value h, which is a distance away from a. Okay. So the arc, equal to 2a plus h, where h cannot equal 0, is a function where h is a variable and a is now a constant. Okay, so a is a constant, some number that we're looking at on the function. So looking just at the average rate of change for h as a function, so I call it arc of h. Okay, it could have been f of h or whatever, but we already had f of x, so call it arc of h, equals 2a plus h, where h cannot equal 0. So we have a function with a hole in it at h equal to 0. So this function looks, well, it's a linear function. Okay, so it's got a y-intercept of 2a. Okay, and if that is the arc, and that is the h-axis, and then it has a slope of 1, okay, like that, but it has a hole in it right there. So that is really just a polynomial in h. So the limit of that is really easy. Okay, it's going to be 2a. The limit as h approaches 0 of that is going to be nice, and it's going to give you 2a, and then you've got the instantaneous rate of change. Okay. So in determining the arc, we seem to get functions with h as a variable and undefined at h, well, at h equal to 0, so h cannot equal 0. Okay, so it should be undefined at h equal to 0, therefore h cannot equal 0. Okay, so we often get things that look like this. So we get a hole at h equal to 0. So if that is the arc expression, all simplified, where h is the variable, we will always have this hole in it at that point if the instantaneous rate of change exists. Okay? So the limit of these exist even though the function doesn't, so the arc function doesn't, because of it's not continuous there, but the limit does exist because if you had filled in that hole, it would look like it's continuous. Okay? So in this case, we've got that the instantaneous rate of change of f of x equal to x squared at x equal to a equals 2a. Now that's convenient because in the past examples, we've always had a value. We didn't just leave it as a. Now we have basically a general formula for x squared. So when we want to find the instantaneous rate of change of x squared at 1, I would just put 2 times 1 here, so it's 2. The instantaneous rate of change of x squared at x equal to 7 is going to be 14. 2 times 7 is 14. So you don't have to go through that process over and over again if you have that general formula. Okay. So we're going to look at this one now using this value. So for determine the instantaneous rate of change at x equal to a for f of x equal to x cubed. Well, we've got this expression here again, and now we have a difference of cubes on the top. Okay, so we've seen that formula already. So let's look at it here. Well, we're going to expand that out. Actually, it's not factor it. Okay, so we're going to expand that out, and the a cubes go away. And then what we have left in here is always an expression where each term has an h in it. Okay, so we can divide out the h. Once we cancel those out, then we get this nice polynomial in h. Remember, a is a constant, h is the variable. So the limit as h approaches 0, well, this goes to 0, this goes to 0, and we end up with 3a squared. Okay, so that's nice and convenient. We now have a formula for the instantaneous rate of change of x cubed at some value a. Okay, so at 0 it would be 0. At, say, 3, well, 3 squared is 9 times 3 is 27. So the instantaneous rate of change of x cubed, which looks like this, at, say, 3, instantaneous rate of change there is 27. So the slope of that tangent there is 27. We said at 0 it was going to be 0. So there the instantaneous rate of change is 0. Okay. What about this one? 1 over x. Okay, so for this one we've got that nice expression again. And flip that over, subbing in a plus h into x and a into x. We get this. We then look for a common denominator. Okay, and instead of dividing by h, I'm pulling 1 over h out in front. Common denominator, multiply this one by a and this one by a plus h. We've got that expression. Simplify the top. We've got that one. Now we can cancel out the h's. And when we do that, we get negative 1 on the top and this expression on the bottom. Now we can just substitute in h equal to 0 because it's continuous around that, as long as a doesn't equal 0. Okay, because we know that this function does not exist at x equal to 0, so we can't have a equal to 0 in here because that would not be allowed. So we got negative 1 over a squared. So that is the instantaneous rate of change of 1 over x at any value a for x. Okay. And we'll go to this next example for one that we've looked at before too, the root x. Okay, so root x, well, now we have this expression here. We're going to multiply by the conjugate. Okay, so multiply by the conjugate because it's a difference of squares. Then it becomes this squared minus this squared. Okay, we get that expression. We simplify it, the a's go away. Then we cancel out the h on the top and the bottom. Got this one now. We can take the limit as h goes to 0. And it's 1 over root a plus root a, 1 over 2 root a. Okay, so for root x, this is what the instantaneous rate of change is at any value a for x. Okay. So couple of examples. These are questions from the textbook. Okay, so in this question here, it's page 1821. They're asking for what is the value of x for when the instantaneous rate of change of this, or the tangent of this function. Remember, instantaneous rate of change is the slope of the tangent. So when the tangent of this function is parallel to y equals 8x. Well, y equals 8x has a slope of 8. So parallel to that would mean that the tangent to this has to have a slope of 8. So the instantaneous rate of change equals 8. We want to find x. Okay, so let's take a look. So first of all, we have to determine the instantaneous rate of change of that function at some value x. Okay, so now x is unknown. We're going to try and find that. ERC is going to equal to 8. Okay, so we do the instantaneous rate of change for all of this. Keep evaluating down. Okay, so at this point we've gotten rid of the h on the bottom. Okay, and we have just that polynomial, so I can get rid of that division line too. And when we take the limit, that second term goes away, and we get 6x minus 4. Okay, so 6x minus 4 equals 8. Solve that equation, and you get x equal to 2. Okay, so the question asks for the point where this happens, so you've got to sub x equal to 2 back into the original function to find the y coordinate, and then you can say that the point where the slope of the tangent, or where the tangent to that function is parallel to y equals 8x, is 2, 4. Okay. Now we're going to look at number 22 on page 18, and it is, let's see here, we've got this ugly rational function, and it's this one right here, number 22. Okay, so 1/3 x cubed minus 5x minus 4 over x. So find the slope of the tangent, where, or find the points where the slope of the tangent is horizontal. The tangent is horizontal. So when the tangent is horizontal, okay, then the slope is 0. So first of all, we need to work out this problem here. So I'm going to just push it through the video. You can stop and try it and check your answers. Okay, so this is how it's all working. And we get the instantaneous rate of change is this expression. Okay, so the tangent is horizontal when the instantaneous rate of change is 0. So when the instantaneous rate of change is 0, we got to set that equal to 0. You solve that equation, and you get difference of squares. So here I've multiplied both sides by a squared to get this. And then we factor it all out, and we get a equal to plus or minus 1, plus or minus 2. Sub that into the f of x so we can get the points. And we get all these values here, and then these happen to be the points where the tangents are horizontal on that function. Okay, so that's number 22. And number 24. 24 says determine. Okay, so 24 says determine the equation of the line that passes through 2, 2 and is parallel to the line tangent to that at that. Okay, so we need to find the equation of the line that goes through that. So it has that as a point and is parallel to this tangent of this function at that. So we need to find the slope of that tangent. Okay, so we need to find the slope of the tangent of this function at that point. Okay, and here we go. I'm just going to show this to you. Okay, and you can work it out and check it on your own.